All right, in today's video, we are going to learn how to write electron configurations. So we need our periodic tables handy, and we really need to be thinking because this is a huge topic and this is going to be very different from the way that we wrote them in Regents. All right, so to start with, in Regents, if we had, say, sodium, its electron configuration is 281. We can gather a lot of useful information from there. We know that there'd be our nucleus surrounded by 3 electron shells. There'd be 2 electrons in the first ring, 8 in the second, and 1 in the last shell. So we know that we would have 1 valence electron, 11 electrons total. Again, we can get a lot of useful information from there. We are now going to be writing big kid electron configurations. And with our big kid electron configurations, it's going to look like this. 1s2, 2s2, 2p6, 3s1. So that's going to be sodium. So what these numbers mean, these big numbers here represent the electron shell. So first electron shell, these are in the second electron shell, third electron shell. So we can still see that we have 3 electron shells. Then we have these letters. The letters represent the sublevels. These sublevels are given by the letters S, P, D, and F. And we talked about those in the previous video about their shapes a little bit. Then our superscript gives us the number of electrons present in that sublevel. So we have the first energy level, S sublevel contains 2 electrons. So there's still 2 electrons in the first shell. Then we have second electron shell, S sublevel, has 2 electrons. Then also in the second shell, in the P sublevel, we have 6 electrons. So we still have 8 electrons in the second shell. But now we know that they're split up into the S and the P sublevels. Then in the third electron shell, S sublevel, we have just 1 electron. So we still have the 1 valence electron in the third shell, but we are a little bit more specific on the location, knowing that it's in the S sublevel. So now we're going to go through some of that stuff in more detail, but I'd like to start this with an example. And honestly, it looks a little crazy at first, but it's pretty straightforward and you'll get the hang of it after doing a couple of examples. All right, so first energy level just has 1 sublevel. The only sublevel in the first energy level is S. The S sublevel only contains 1 orbital, so we can have 2 electrons in there. So we have a total of 2 electrons in the first energy level. In the second energy level, we have both the S and P sublevels. In the two electrons in the S sublevel and 6 in the P sublevel to give us a total of our 8 electrons that we know can be held in the second energy level. In the third electron shell, we have the S, P, and D sublevels. S can hold 2. That's all it has space for. P is bigger. That can hold 6. D is bigger, can hold 10 electrons total. Therefore, the third energy level can hold up to 18 electrons. The fourth energy level has the S, P, D, and F sublevels. S holds 2, P holds 6, D holds 10, and F holds 14, giving us a total of 32 electrons that can go in the fourth electron shell. Okay, now let's go back and talk about this orbitals column. So this dealt with the video yesterday. S sublevel just had one orbital, can hold 2 electrons. So S has one orbital. P, though, has 3 centered around each one of those different X, Y, and Z axis. Each one of the 3 orbitals can hold 2 electrons. That's what gives us the 6 total. So S has one orbital. Each orbital holds 2 electrons. P has 3 orbitals. Each orbital can hold 6 electrons. Each orbital can hold 2 electrons, giving us a total of 6 electrons. D has 5 orbitals. Each orbital can hold 2 electrons. That's how we get to the 10 total. So S, one orbital, can hold 2 electrons. P has 3 orbitals. Each orbital holds 2 electrons, giving us 6 that can go into P. D has 5 orbitals. Each one of the 5 orbitals can hold 2 electrons. That's how we get 10 electrons that can go into D. So D has space for 10. F has 7 orbitals. Each orbital can hold 2 electrons. That's how we get the total of 14. So yesterday when we looked at their shapes, S was just a sphere, doesn't have a whole lot of space. F had a whole bunch of different orbitals. That's why it can hold the 14 electrons. So each orbital can hold 2 electrons. This is just a summary of that chart. It's the exact same thing, just, filled in there. So again, first level has just S. Second level has S and P. Third has SPD. Fourth level has all 4 of our sublevels. And then that's how you get the different amounts. All right, so if we continue our chart here, the 5th electron shell can also have S, P, D, and F. S has the 1 orbital, 2 electrons. P has 3 orbitals, 2 electrons in each, giving us 6. D, 5 orbitals, 2 electrons in each, giving us 10. F, 7 orbitals, 2 electrons in each, giving us 14. That totals 32 electrons that can go into the 5th electron shell. After the 5th, it starts decreasing. So the 6 has S, P, and D sublevels. S has 1 orbital, can hold 2 electrons in that one sublevel. P has 3 orbitals. Each orbital can hold 2 electrons. That gives us 6 electrons total that can go in a P sublevel. D, 5 orbitals. Each orbital can hold 2 electrons, meaning 10 electrons can go into a D sublevel. This gives us a total of 18 electrons that can go into the 6th energy level. Lastly, in the 7th, we are down just to S and P. S has 1 orbital, 2 electrons can go in there. P, 3 orbitals, 2 electrons in each orbital, giving us 6 electrons. So we can only have 8 valence electrons are 8 electrons in the 7th energy level, which also would be the valence electrons too. So again, this is what we saw on our first slide. So we're going to be writing electron configurations like this. The coefficient gives us the principal energy level or electron shell. So we have electrons in the first shell, second shell, third shell. So this would be something in period 3. The letter gives us the sublevel. So first electron shell, S sublevel, contains 2 electrons. So the superscript tells us how many electrons are in that sublevel. So we have 2, 4, 10, 12. We have 12 electrons. So if this is an atom, this would be magnesium. All right. If you use your periodic table to do these, it becomes much easier. So let's take a look at our periodic tables and let's actually label some stuff on our periodic tables. So group 1 and 2 is what we call the S block. So anything in group 1 is going to end with its electron configuration being S1. So for example, if we're potassium here at atomic number 19, it's going to have its electron configuration and then it's going to end with 4s1. Anything in the second group is going to end in S2. So notice the S block, 2 columns wide because S can hold 2. The P block can hold 6 electrons, or the P sublevel can hold 6 electrons, and lo and behold, the P block is 6 columns wide. So it's going to be P1, P2, P3, P4, P5, P6. So wherever you are in here, like if we're down here at 85, the electron configuration is going to end in 6p, 1, 2, 3, 4, 5. So it's going to end in 6p5. This can also help us remember that P can hold 6 and that S can hold 2. All right, D block here. D can hold 10. And D is 10 wide. So if you are going to be doing the electron configuration for this atom here with an atomic number of 44, it would be D1, 2, 3, 4, 5, 6. And then F block, F can hold 14, and this is 14 wide. So we're going to use this to help us. So let's look at some examples. So let's start with aluminum. Aluminum is atomic number 13 and would be right over here. All right, so when we start our electron configuration, we have to start at 1. And you literally kind of trace your finger along the periodic table. So that would give us 1s, 2. So we got to start with the first energy level, S sublevel, 2 electrons. And then we keep going. Our next thing that comes up is 2s. Since it's an S, we can put in 2. Then we hit the 2p, and P can hold 6. So that takes us up through neon. So we've placed 10 electrons. We still have 3 more to go. So then we keep going. 3s, or S can only hold 2. Okay, we got 1 electron left, and that's going to go into 3p. Now P can hold 6, but we only have 1 electron, so we end with 3p1. So that's how we figure out the electron configuration for aluminum using the periodic tables. And we still get the same information that we would have gotten from reagents. We have 2 electrons in the first shell. We have 8 electrons in the second shell, and we have 3 valence electrons in the third shell. All right, we're going to do another one together on here. We are going to do iron. So iron is atomic number 26. So we'd be, right about in there. So we're going to start 1s2. Okay, that's always where our first 2 electrons go. Then comes 2s, 2. Then we keep moving. We get to 2p. We can put 6 electrons in there. So we've placed 10 electrons so far. So got 16 more to go. Then next up is 3s. Since it's an s, we can put in 2 electrons. Then we got 3p, 6. Okay, next up is 4s. Since it's an s, we can put in 2 electrons. So we have placed 20 electrons so far. We have 6 left. Okay, here's our tricky thing. When we go into the D's, it goes back 1. So we just put 2 electrons in the 4th energy level. Now we go back and we add some into the 3rd energy level in the D sublevel. Do not obsess over this. Just accept the fact that the D's are 1 back. The reason is because even though it's a lower number, it's actually a higher energy sublevel, but just accept it for what it is. When you get to the D's, it's 1 back, and the F's are actually 2 back. So then we do 3D. D can hold up to 10, but we don't have 10 electrons. We only have 6 electrons, so we would end at 3D6 for iron. Again, we still have 2 electrons in the first shell. We have 8 electrons in the second shell. Third shell gets a little tricky. We get 8 electrons plus those 6 in the 3D. So we actually have 14 electrons in the third shell and 2 valence electrons in the 4th shell. So these ones, even though we did not write them last, are still the valence electrons. 4 is 4 is 4 is bigger than 3. So even though we did not fill these last, the 4th energy level is still the furthest from the nucleus. So again, the 3D would get counted with the other 3s for the total number of electrons in the third shell. All right, so now we're going to do some more examples. You definitely need to be looking at your periodic tables in order to do these. So first one we are going to do is cadmium. CD right next to silver, right below zinc, atomic number 48. So you start at hydrogen, 1s2, then 2s2, then go over to 2p, p can hold 6, then comes 3s, and it's an s, so it holds 2, then we get 3p, 6, so we have now added 18 electrons. Keep going, we got a lot more to do. 4s2, then we get into the D's. Remember, D's, they're just 1 behind. So we do 3D10 because we move all the way through that D block. Then we come out on the other side of the D block, go to 4P. That can hold 6. So right now we've placed 36 electrons. After 4p, if we keep following atomic number, we go to 5s2, and then we go 4d, because now we're back in the D. D's got to be 1 back, and we count over how many spaces are we in the D block, and we count over we are 9 spaces in the D block. And that should, oh, I'm sorry, we are not 9 over, we are 10 in the D block. So that should give us our 48 electrons total. But if they were asking for how many valence electrons, highest number, 5. These are our 2 valence electrons. So 5s2, we would only have 2 valence electrons here. Yttrium, that is Y, and that is atomic number 39. So we got 39 electrons. We always start at the same place, 1s2. Okay, move across, 2s2, keep going, 2p, that can hold 6, 3s2, 3p6, so that would bring us to argon's spot in the periodic table, so 18 electrons. We have to keep going, 4s2, then we get to the D block. D is 1 behind, 3d10, go into 4p, 4p6. Next would be 5s2, and then 4d1, because we only have 1 valence electron left. So we just get more information from these electron configurations. Not only do we know what shell they're in, we know what sublevel the electrons are in. All right, the last one, iodine. And that is atomic number 53. So we got 53 electrons. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Then we go into D. D is 1 behind, 3d10, 4p6. After 4p would come 5s2. Then we would do 4d10. So this would basically take us up to cadmium, or up to cadmium, which we had in the first example. And then we would be 5p, and iodine is 5 over, so 5p5. And that would be it for iodine. If they asked us how many valence electrons, we already know group 17 has 7 valence electrons. 2 in the 5s, 5 in the 5p. So we have 7 valence electrons total, because these ones here are in the 5th energy level. All right, on iodine, you were probably getting a little bit bored of, writing out all that beginning stuff like 1s2, 2s2. So there is a shorthand that we can do. It's called the noble gas shorthand. So what you do is you write the preceding noble gas in square brackets, and then just everything else that comes after that. So this would be the electron configuration for basically neon plus 3s2, 3p5. So if you follow along in your periodic table, that would give you chlorine. Okay, so we'll try this real quick with calcium. So calcium, Ca, atomic number 20. So we got 20 electrons. So you go to the preceding noble gas. So that would be argon. So square brackets, Ar. And then so it's basically saying calcium's electron configuration is everything that's in argons. Then additionally, we would have 4s2. So if we took an if we took a quick look at iodines that we had on the previous slide, the preceding noble gas to iodine would have been krypton, Kr. Okay, so it would be Kr plus everything after that. So 5s2, 4d10, 5p5. So that's going to save you a lot of time on those longer ones. If you feel like you want a little bit more practice, you can go back to some of those previous examples that we had done and write the abbreviated electron configurations. We are going to have some practice problems in our packet at working on this, and then we have another thing to look at with our electron configurations where we do orbital notations as to how the electrons are arranged within the orbital.